was sitting here thinking, oh, it wasn't that long ago that I was a student working on a project very similar to this, the new bio project. But then I think back, and heck, I've been at the INL now for 7 years. So it's been a while since I've been out. And yeah, while my background is primarily in forest resources and forestry and that area, what we're going to focus on primarily today is looking at herbaceous biomass. We will get into woody a little bit, but really what we're going to talk about is the impacts of feedstock variability and pre-processing and those impacts along the supply chain and how we mitigate those issues. So just to start off, we're going to kind of define the problem that we're talking about. And so we have a challenge with biomass feedstocks, particularly, that there's inherent variability within the material. And that affects our ability to optimize the processing, and then that spills over into the conversion process. So if we're trying to make products or fuels, and you have a variable product, it makes it very hard to optimize your plant, and that affects plant economics, then ultimately affects the cost of the product that you're producing. So as biomass researchers, and especially along the supply chain, what our goal is to maximize the economics of the biorefinery by having better process quality control. That's putting better feedstock into the system, so that we can have predictable yields and know what the plant is going to produce based on what we're putting into it. And it's not a guessing game. And so to be able to do that, what we need to be able to do is control several factors. And this is where it gets a lot different than, you know, an oil or a coal or chemical facility. So we have variability on very different fronts. So first, we have to be able to control the composition of the material, make sure that we're getting a consistent composition, because that leads directly to yield. Particle size distribution, that leads to convertibility and losses in the system. So if you have material that's too small, you can overtreat. It can get pulled out of the system through dust collection, that sort of things. Low properties, we're dealing with a material that is geometrically irregular in many times. And so it makes it hard to flow through the system. It's not a liquid, it's not a powder per se. So it makes it hard to efficiently, and we're going to talk a lot about that coming up. And then we look at just the inherent properties of the material, specifically in this case, moisture and ash, things that we can control to a certain extent, but has significant impacts in the system through the way of causing failures in the system. Either excessive wear or moisture is something that generally leads to blockages in the system. And so what we're ultimately trying to do is lower the mean cost of material based on controlling these factors also. So instead of taking the approach of we're just going to throw everything in and see what we get, what we will present towards the end of this talk is our thoughts on how we reach a material that can be usable in the system. And that's going through a process of fractionation. Then we reformulate that material to meet a specification. And then whatever's left over, we try to find ways to use it in alternative markets or conversion processes. So starting off with variability, this is the variability of corn stover standing in a field. You can see there's really what we can what we're concerned about from a conversion standpoint, especially the fuels. What we look at a lot at the Idaho National Laboratory and across the National Lab complex is a fermentation route. So we're looking at the importance of total sugars. Lignin for co-products helps the economics a little bit, or is thought to. And then ash, which tends to buffer the conversion process. And so we see as standing in the field, ash is relatively low. We're generally below 5% standing in the field because the only ash that you have is intrinsic to the material. But even standing in the field, the goals that we're looking at for making conversion economic, we're only meeting that about half the time. And then lignin, we're probably a little bit higher than that in the field. And all this data was based on a study done looking at hundreds of stover samples by Templeton et al. At NREL in 2009. But then, this is standing in the field, but you have to harvest the material. And so whenever you harvest and you store the material, because there's a finite harvest season, usually about 3 to 6 months, and you have to store that material to be able to have it available for the entirety of the year. You introduce more variability into the system at that point. So the harvest method can introduce ash. So you're going to potentially pick up some soil during the harvest. You're going to have some degradation during storage, which will also enhance ash because ash will not break down. And so as you're breaking down your carbohydrates from microbial activity, your ash would potentially go higher. Material enters at a moisture that generally can be unstable for it to be stored for a long period of time. So you're going to get some self-heating, you're going to get some microbial activity that leads to degradation in that stable material. And then as you have it in a stack, as you see in this picture, on the lower picture, moisture is going to start to migrate through the stack. And so you're going to get, if everything went in at say 30%, as the moisture migrates with it sitting there, based on airflow and different things, you're going to start to get bales that are very high moisture, 40, 50%, and you're going to get some that dry out. And what this does is some of the self-heating and the way moisture moves around, it changes how you can mechanically deal with the material, how it breaks down, how you can handle it in grinders for size reduction, even if you can put it on forks and get it into your plant because of some of the degradation. And so those are some of the issues that you deal with just on the very front end from variability within the feedstock. So what this chart shows is, in the blue is the same standing compositions. You can see how after harvest and storage, how those distributions start to widen out. You start getting wider distributions in your sugars, lignin widens out, and that's all as a part of how much degradation happened in the system. One to really look at is the ash. So at this point, you're no longer just looking at intrinsic ash to the material, which is at 3 to 4 to 5%. You're now picking up ash on the bale. So if it's muddy out or it's wet when you're harvesting or picking up bales, you could have mud stuck to the bale, gets trapped inside the bale, and so now you're looking at 50% ash on some of the material that's coming in. But the moisture distribution stays relatively unchanged. It's still very wide though across the system. So we're dealing with that sort of variability as it comes into a processing system. And what we've done historically is treated it like making hamburger or sausage, I guess. We take the whole animal, or in this case, the bale, and just want to size reduce it and homogenize it so it looks the same. And we were hoping by doing that, what we were going to increase was being able to handle the material better. And we were able to, densify and make pellets, but you still have the inherent variability within the material. And so while you can get the material through your system a little easier, the quality is very different, or can be. And so ultimately what you want to do is be able to convert your best material or your most ideal material. And so that's where we get back into this fractionation approach later, is if you process it in such a way that you're homogenizing the material from size at the beginning, it makes it very hard to extract your high quality material. So one of the things that we say around the INL is, is trying to go back in and get your high value steaks, your filet mignon, or your porterhouses back out after you've ground it all into hamburger. It's not really a possible thing to do. And so what we've seen is with traditional harvesting practices, we're not really able to impact the quality very much. You can see there's a slight shift. We've slightly increased the carbohydrate content by removing some of the ash material, but still the distributions are very wide. And so of the material that comes in, we know that about 11% of it meets the specs that we're looking for. But as we go forward, so we're looking at a lignin spec and a carbohydrate spec here, only about 20, we were able to increase that 11% up to about 29%. And the way we've looked at this is through use of modeling. We've used what's called discrete event simulation. I don't know how many of you are familiar with that type of modeling. But what we've done is created a discrete event simulation where we're sampling biomass coming into the facility at 1 ton aliquots of material, and then processing and looking at how those change through the process and how the material or how the process operates across time. And so, we're able to meet the total sugar spec. So that's 59% or greater carbohydrates. We're able to meet that 44.5% of the time. The lignin spec, which is 15.8% of the total mass material being lignin, we were able to meet that 54% of the time, but we were only able to meet both simultaneously 29% of the time in this case. So, and that's the quality impact, is we're very rarely meeting the quality needs that we need to have to meet our yield goals. But additionally, we have feedstock properties that are impacting us operationally. And so on the left here, we're looking at a screw feeder, a plug screw feeder. So it's needed to build pressure going into the reactor to make sure you keep your pressure up for the pre-conversion process. When you have high ash material, you tend to wear your screws. And so at the top, you can see the sharp edges basically, on a new plug screw. And the bottom is the same one after 54 hours of operation with kind of your typical high ash corn stover coming out of the field. And you can see the wear that has happened and how that would affect the ability to keep a seal, which not only affects your throughput at the time, but can then lead to a dangerous situation where you have blowback through your reactor, causing just complete process upsets there. On the right-hand side is some pictures from, I believe this is the Abengoa plant that was in Southwest Kansas. What you see is, just plugging and rat holing coming from high moisture material trying to be moved through the system. So in the top picture, you can see there's a hole there where some of the material fed, but then the rest of it's just kind of stuck there. And then the bottom picture is the plug screw feeder that they had there and the material that they had to pull out because it got jammed. The guy that had these pictures told the story of there were a couple times while they were working on this plant that they were, shaking it down, and that the plug screw would get jammed so bad that they'd have to bring in locomotives to extract the screw from the casing. It required that much force to get it out. And so for no other reason, I imagine renting a locomotive to pull things out of your plant is not cheap. So that would be a definite hit to your economics over time. But we can quantify the impact that these factors would have on the system. So these pie charts look at the impact of moisture and ash on downtime. And so we can see that moisture causes the vast majority of down events. So you have material that is too wet going into your system, and it causes those bridges, causes your grinders to plug. And so if you have lots of bales that are outside of your moisture parameters, you're gonna spend a lot of time cleaning out grinders and slowing down your operation or stopping your operation. But while they're 2/3 of the downtimes, that accounts for about 90% of the total downtime that you have. You can see that the next case where regular downtimes or just typical machine breakdowns account for about 1/3 of your downtime, of your down events. It only accounts for about 3% of your total downtime, where the wear and the time that it takes to replace and screws and things that wear out due to ash become a lot more significant, even though they are a small fraction of what actually occurs. And another consideration that we have with current and way that processing is generally done still to this point is we tend to over process a lot of material. So a lot of plants use what is called a two-stage grinding system. So you bring in your bales of corn stover. You first break the bale with a big grinder just to get it into a little more of a flowable, loose form. It then goes to a second stage grinder where it's reduced to size that you want to feed into your reactor. But by doing that, you're not accounting for any size reduction that really happened in the first case. And so if you're trying to get to a 1/4 inch to 8 millimeter size particle, you end up having about more than half of the material that gets over processed and then becomes too small, which would lead to applying chemicals. You're applying too much chemical likely, so you're over treating the material. If it would be a thermal application, your heat rates would be different. So that would be a concern. So you've basically lost half of your material, or reduced the yield on that material because it's now too small. So, like I said, we've simulated these systems. Generally, the way we do it, we simulate them for a year of operation. And this is the results of some of the simulations. So what we're looking at is the daily throughput of these facilities. And what we're seeing is from the high moisture material, from the ash that comes in, this is really without doing anything to mitigate. It's basically as the first biorefineries operated, we're looking at about a third of the daily capacity. We're averaging about 670 dry tons per day, where a facility would want to get, 2205 short tons per day, 2,000 metric tons per day. As with anything, your throughput's going to vary over time, plus or minus 51 dry tons per day or so. You're going to have good days and you're going to have bad days, but when you're averaging a third, I guess none of them are really good days at this point. Your economics are not great. And we were able to even validate this model a little bit. So with the pioneer biorefineries that were out there, there was a Tiger team that went and was assessing why, they weren't working. And if anybody knows now or is following it, none of them are in operation. And what we were able to find out by talking to people that were involved with that is we were within 5 or 10% of what those plants were actually operating at with our model. So we feel pretty confident that we're able to draw some pretty strong conclusions with what we were doing. So you have that daily variability, but this is looking at the individual units of material that come through and what it cost for a feedstock. This is making it to the conversion reactor. What it costs to get the system or get material ready for conversion. And so what we can see is, we have a mean cost, still pretty expensive. And most things that we work with are looking at, cost $70, $80 a ton. We're $182 a ton at the mean. Our cheapest stuff, makes it through right around the target that we're looking at, the $83 a ton. But you have material that gets stuck in the system or slowed down because of degraded performance caused from the feedstock, and it takes so long to get through the system that it costs, $10,000 a ton, and so that can really wreck your economics that way. I'm not sure. I guess I haven't checked yet if we have any questions. I'll get to that in just a second. But that variability in cost also, then cascades down to the cost of your final product, right? So in this case, we're looking at biofuel costs, so dollars per gallon of gasoline equivalent. In this case, we have a mean cost of $3.75, but we're getting fuel in the range of $1.33 to $239 a gallon. I think if you showed up at a gas station and saw the price was $2.39 a gallon, you would not be pleased in that case. So before we move into the next part of this, if I can bring the meeting stuff back up and see if there are any questions.
Sure. So doesn't look like we have any questions typed in, but I'm curious, could you explain why the plants were producing at only 1/3 of their expected output? Was that due to variability of the feedstock, or were there other factors that were causing it to be so low?
Yeah, there were several factors, variability being the biggest one. Let me get back to my slides here. And so when you have variability, especially in moisture and ash is what we looked at primarily. We have gone to looking at the quality of the material also, but a lot of this is just focused on being able to get material through the plant. And so you have downtime that happens because you plug or you cause excessive wear, and you have to you're replacing knives on grinders every week and a half or so, which takes a couple hours at a time. You're plugging your feeders, which takes roughly a shift and a half to clear out before you can use it again. Then you got to get your system back up to steady state operation. So you're looking probably 2 days of downtime every time it goes down like that. And so, yeah, that there are, aside from that, you also have, you design your plant to work at, say, 20% moisture content. If it fails at 40% moisture content, you have degraded performance between 20 and 40. And so you can get to points where you're like 35% moisture content coming in, and the plant won't shut down. It just feeds at about 10% of what its design capacity is, because it takes longer to process. It's harder to get it to move it through the system. And so it's really, the 33% was really just a feed rate. Had nothing to do with yield of fuel at this point. So hopefully that answers the question. So if there's nothing else, no other questions on this, we'll go ahead and move on. See, time is rapidly ticking down on me. So the first suggestion, or the first thought was, just blend it with a better feedstock. So in this case, we're looking at blending corn stover with switchgrass. Switchgrass, due to the way that it's harvested and when it's harvested, tends to be less ashy than corn stover. It tends not to hit the ground very much, because even when you mow it, there's still a bed there. You're not going straight to dirt. Has a higher lignin content. And so blending those materials, we're able to improve slightly what we were able to accomplish as far as quality, right? So now almost all the material meets the sugar sugar spec, 99.7% of it. 71% of it's now meeting lignin spec, and so now we're getting about 71% of the material in total meeting quality spec, and so that's a lot better than what we were looking at. Ultimately, we're looking to get at least either 100% quality and 90% throughput, or 90% quality and 100% throughput. Either way, to meet the design, that's what you need to meet the economics of the plant. So, and even by blending, we were able to increase our throughput. Now we're hitting at about 50% of the nameplate. So we've added 22% to the throughput. Switchgrass generally comes in drier too, so it's easier to feed. So these are definitely steps in the right direction for plant operation, but we're still not there, right? I mean, still wouldn't want to operate your plant at 50% every day. Make it through. Still have high variability in cost. The average cost went down. We're now averaging right around where we want to be. You still have some very high costs, $500 a ton or so, which is still unexpected. Now your fuel costs have gone down, means $1.51 per gallon. Your high, on your high end, you're $9 a gallon, which still would not be ideal. And so, yeah, we to a certain extent we can blend better feedstocks in. You might say, well, then why don't we just go to 100% switchgrass in this case? Switchgrass is orders of magnitude more expensive than corn stover. Probably not orders of magnitude, but at least double or triple the cost of corn stover out of the field, because of it's a dedicated crop. You're not getting a residue, which is cheap. And so we have to start looking at other ways to handle this material. And so we do that through looking at quality control and how do we start advancing the technology to handle this material. So looking at the raw material, we have this quote from Vice President of Science Global Biologics, that the raw material qualification is extremely important to ensuring process control and final product quality. So what goes in, we can simplify that down to what they say in modeling or any other process, garbage in, garbage out kind of situation. If you're not controlling the bounds of your material going in, you can't control the bounds of your material coming out necessarily. This isn't uncommon in other industries. Natural gas, they remove parts of their the extracted material to improve their quality. They remove water, they remove impurities, condensates. Pharmaceuticals are looking at their non-active raw materials to make sure that they're able to make a tablet that holds together, or a suspension, or whatever. Recycling, they're not throwing paper in with glass and with metal and trying to recycle it all at one time. They're separating the material to make sure they get the best yields, because each one of those processes would take a different process condition. And even crude, we're talking about producing fuel. Fuel out of the barrel of crude oil is a very small fraction. And it's also one of the least valuable fractions that comes out. But they're pulling material off to make lubricants, jet fuel, diesel, lots of greases, that sort of thing, and increasing the value. So what we've realized over time is that the range of variability in biomass is really too broad to be used for a single process. Even if you would turn cows into a stover field to graze, they're only going to eat a portion of it. They generally leave the lower stalk because it's not ideal for them to convert into energy. And so what we've been able to show is there's a demonstrated impact on biorefinery economics. But now, what is the solution to handle that? So what we need to be able to do is move away from kind of the one size fits all processing system. Look at your feedstock. What is the quality of your feedstock? And that can even vary from region to region. Corn stover in Iowa would not be the same as corn stover from Southeast Pennsylvania. Soils are different, climates are different. You'd have to look and potentially treat them different. But what you can do is look at your materials and see what the variability between your different fractions would be. So leaf, and that's one of the big things that you have and that's different in a bale of stover is you have different proportions of fractions. So looking at, we'll say leaf, husk, stem, and cob, how it gets picked up in the field would lead to different proportions of that material, leading to a bale having, if you assume there's very little variability, which isn't really the case, but it's much smaller on a fraction level than it would be on a bale level, you have much higher variability in a bale to bale than you would from fraction to fraction. And so what we're looking at is being able to separate those fractions, process them in the way that they need to be processed, and minimally process them because that improves our costs. It keeps us from over processing, losing material, and then recombining them in some optimal way to get best performance into the system. And things that cannot be converted or aren't appropriate for conversion, we want to send them somewhere else to be used where they would be of more value. So some of this work starts in the field, looking at better ways to harvest, how we stabilize material after harvest. So we've looked at ways to change how we store incrementally with time. So generally the bales that are harvested earlier in the season are wetter, and in most cases they haven't had time to dry down like the stuff later in the season. And so we want to, we've looked at being able to handle that through some drying mechanisms, so infill drying, getting them stabilized. But if we can stabilize the material, we reduce dry matter loss. We don't get that big variability shift that we saw from those first couple graphs that we looked at. The bells maintain integrity, and so we're able to move them easier. It's the whole process more efficient. Then we get into the plant, and we want to get away from, the grinding everything into, sausage or hamburger, and we want to pull off the components. We want to pull off the steaks before we do something like that. And so what this system is showing here is some theoretical system to meet that goal. So you have corn stover bales coming in. It goes into a bale processor, which is different than a big hammer mill. It kind of pulls the material apart. I don't know how many people are familiar with dairy operations or cattle feeding operations. That's what we're looking at, is the things that pull bales apart to feed. We're looking at those as a pre-processing way to create an even flow in the system. One of the big problems that you had with early systems was slugging of material. So if you have square bales, anybody that's familiar, been on a farm, knows that they flake off, right? And so you get big chunks of material coming through the system at a time. Through a bale processor, you have these fingers that are kind of ripping it. You get a little bit of size reduction, but what you really get is an even flow into the system. Eliminate some of that slugging. That goes into a very light hammer mill, if you can have a light hammer mill, I suppose, to kind of break apart the material a little bit. Then we start looking at separation. So the way that we have it here isn't necessarily the way that it would have to be. This is just one method. So we start off with the size separation. Leaf tends to be very fragile. Going through that first part of the system, it will likely break up, become small, and it often is, has a lot of the ash material in it. And so you can pull that off through a disc screen. Material under a certain size falls out. So that would include leaf and ash primarily. And what we see with that in a conversion sense, that material ends up being the least utilized. We use it kind of to balance out the quality because we don't get necessarily a benefit for sending something that is too good, I guess, at least for our economics that we've done.
Damon, we have about 5 minutes left. About 5
Okay.
minutes. Thanks.
So then we separate using an air separator. We can separate husk from the heavier cobs and stalks there. Husk end up getting 100% utilized. From there, you have stuff that are of similar density. Use an optical sorter. Cob goes to a knife mill, so you can size reduce it. You're using the majority of that material. There's a little bit left over, and then you size reduce the stock, and then you can recombine those materials to produce a more ideal conversion material. So here we start off looking at bales coming in versus bales after storage. Be very similar. The moisture is a lot less. Ash is reduced because we have that blended material, or because of how we're handling it. But by blending it back in, then this is probably a little ideal. We're able to close those distributions down and deliver a much more consistent product to the biorefinery. In this case, we were able to end up meeting everything on quality and throughput, while you still have some ups and downs because you're still going to have machinery break and that sort of thing. We even get days where we're above the design, so we actually get to meeting our throughput targets for the year. Still have a little bit of variability in cost, but it's very small compared to what we were looking at before. With a cost of about $73 a ton, and then for between $1 and $2 for the gas. With supply chains, it's really not so much of an issue for throughput. It's really the quality and being able to get ash, and especially when we're looking at just logging residues. I'm sure that these slides will go out, I hope. So you can look at these, and we're going to kind of breeze through the woody side of it. Like I said, throughput ends up being not a huge issue. And you still have some of your material that's caught in there, but because we're only processing certain, so yeah, if you look through here, we're separating material in an air classifier. The high ash material goes through a chemical leaching system and is recombined, and that allows us to only process a certain fraction of the material and meet our targets of 90% meeting the quality spec and our throughput. That gets us to the cost. On average, we're $70 a ton. So just in summary, like I've mentioned, conventional methods tend to overprocess material. You have a hard time separating stuff of good quality from poor quality after you've done that. And so, we go back and look at the pioneer biorefineries and supply systems. Introduced variability is a significant contributor to performance issues in the system. you know, the plant in the field is good. It's all the stuff that we do that makes the system work, that also increases variability. You know, looking at harvest systems that reduce the contribution of ash, finding better ways to control moisture, that sort of thing. And just because you're able to meet capacity doesn't mean that you're able to meet all your targets, because there's still a quality component. If you're not meeting your quality sufficiently, it doesn't matter how much material you push through, your costs are still going to be high. And so by fractionating the material and minimizing that quality variability, we're able to tailor the processes to meet feedstock goals. So with that, I think I still have a couple minutes for questions, hopefully.
Sure, we have time for a question or two. Anyone here in the classroom has a question they'd like to ask, or if you're online, you can click the raise hand button and we might be able to turn on your microphone. Here, Hannah, you have a question.
So I know you said about moisture causing the largest impact on downtime in an event. So should like the facility spend money or time drying the feedstocks beforehand if they're like at a certain threshold? Like, would you recommend that, or do they even do that?
Yes. So we've done work. We have a project that looks at drying and field drying. And what we've seen is, you know, the added cost. We could even put fans in to blow air across certain stacks of high moisture bales, and it pays for itself through the increased throughput and reduced downtime of the system. And so that is a way to do it. Practically, if a biorefinery is taking bales from the market, so they have farmers bringing them in, they could, you know, just reject bales that don't meet the quality specs. But that's more of a business case. But there is adequate information to show that you can pay to physically dry some of the material and not adversely impact and even help your economics over time.
Thank you.
Okay, terrific. Well, I think we'll just leave it at that. So Dr. Hartley, thank you so much for taking the time to share with us today's seminar. I assume that if people have additional follow-up questions, they can contact you by email. Would that be okay?
That would be perfectly fine.
All right, terrific. So thank you so much. Really appreciate it, and look forward to seeing all of you at next week's seminar as well. Thank you.